In this video, we are going to talk about the properties of exponential functions. In general, we are going to consider the exponential function of the form y equal to ab exponent x, where b is any number, any real number greater than 0. First of all, if b is equal to 0, then it's going to be y equal to 0, which is going to be the x-axis. So b can be any positive number greater than 0. Now let's consider each case separately. For instance, let's assume that a is positive and b is also positive, but b is a number which is greater than 1. So a is positive and b is greater than 1. Let's see what will happen. Let's assume that b is a number greater than 1. Let's say that number is 2. Then we are going to have y is equal to a times 2 exponent x. The reason I'm assuming that b is 2 is for you to understand what will happen if b is greater than 1. Any number, let's say 1.5, 10, whatever. If we want to plot this one, remember that for plotting exponential functions, we are going to consider three cases. When x goes to plus infinity, when x goes to negative infinity, and when x is equal to 0. Let's consider x equal to 0. Then we are going to get y is equal to a times 2 exponent 0. We know that 2 exponent 0 is 1, so this means that y is equal to a. And we know that a is a positive number, so it's going to be somewhere around here. So let's assume this is a, and this is the y-intercept. Now let's assume that x goes to negative infinity, meaning somewhere around here. When x goes to negative infinity, then we have y is equal to a times 2 exponent negative infinity. We know that with negative exponents, we can just flip it, and then it becomes positive exponent. Now 2 exponent negative infinity is the same as 2 exponent negative infinity over 1. When you flip it, you get a times 1 over 2 exponent infinity. Now 2 exponent infinity is going to give you an infinite number. Let's say 2 exponent 1000. That's going to be a huge number. And any number divided by a very big number is going to give you 0. So this means that this one is going to become a times 0, which is going to be 0. So this means then that when x goes to negative infinity, y goes to 0. So it's going to be around here. Now you may say, oh, what about not here? Because here is almost 0. The reason is the y-intercept. Since the y-intercept is over the x-axis, so this 0 is the one that we have to consider. So we have this point, we have this point, the y-intercept. What about when x goes to plus infinity? Then we get y is equal to a times 2 exponent plus infinity. 2 exponent plus infinity is going to give us plus infinity times any number is going to give us plus infinity. So this means that when x goes to infinity, which is here, y goes to plus infinity. So it's going to be this point, somewhere around here. Now connecting these points together, we get a graph like this one. Before we consider the next case, let's look at the domain and range here. You can see that the domain is any x value. So we say D is x such that x in R. There is no restriction on the x value. But the range is going to be y such that y is in R, and you can see that y is always above the x-axis, so it means that y has to be greater than 0. And y can't be 0 because the x-axis is your horizontal asymptote. So the range is y greater than 0. Now let us consider the next case. Let's say in the next case, a is greater than 0 still, but this time b is between 1 and 0. Let's assume b is some number between 0 and 1, let's say 0.5. So we get y is a times 0.5 exponent x. Again, let's consider three cases. When x goes to negative infinity, when x is 0, and x goes to plus infinity. So let's have our coordinate system here. When x is 0, then any number exponent 0 is 1, so we get y is equal to a times 0.5 exponent 0, which is a times 1, which is a. So again, since a is greater than 0, so it's going to be somewhere around here. So let's say this is a. Now let's consider when x goes to negative infinity. So y is a times 0.5 exponent negative infinity. Now, we know that 0.5 is 1 over 2, so I can write this one as y is equal to a times 1 over 2 exponent negative infinity. But we know that when it's negative exponent, we can flip and get a positive exponent. So this is the same as a 2 over 1 exponent positive infinity. Now, 2 over 1 is the same as 2, so 2 exponent infinity, we know is going to be infinity, times a, which is a positive number, is going to give us positive infinity. So when x goes to negative infinity, which is somewhere around here, y goes to plus infinity. So it's going to be somewhere around here. Now let's assume that x goes to plus infinity. So we are going to have y is a times 1 over 2, which is 0.5, because we are assuming that b is 0.5, exponent plus infinity. 0.5 to a positive infinity is going to give us 0. I mean, the way you can find out is you use your calculator and say 0.5 exponent, let's say 100. Then you will get a very, very small number. So this means that when x goes to infinity, plus infinity, which is somewhere around here, y goes to 0, which is here. So connecting the points together, we're going to get something like this. Now, this is telling us that for the case that b is between 1 and 0, the y-intercept is the coefficient here, which is a. The x-axis is our horizontal asymptote. The domain, again, is there is no restriction on x, so the domain is all the real numbers. And the range is all the y's which are in real numbers, but they have to be positive. So y has to be greater than 0 and not equal to 0, because y equals 0 is the x-axis and that one is the asymptote. So this was case 2. Now let us consider the third case. In the third case, we are going to assume that a now is negative and b is greater than 1. Again, let's consider the case that b is 2. So y becomes a times 2 exponent x. Again, let's try to plot this graph. Now we are going to consider when x is 0. When x is 0, 2 exponent 0 is going to give us 1, so 1 times a gives us a. And since a, remember, by condition is negative, so this means this time a is somewhere around here. So this is our a. The next case is when x goes to negative infinity, which is here. Now, we are going to have y is a times 2 divided by 1 exponent negative infinity. Since it's negative infinity, I can flip it, and I get 1 over 2 exponent plus infinity. We know that 1 over 2, which is 0.5, exponent a huge number, is going to get closer and closer to 0. Use your calculator, find 0.5 exponent, let's say 100. Then you will see that this exponent is going to give you 0 times a gives you 0. So this means that the tail of your graph is going to be here. Now, let's consider the case when x goes to plus infinity. So we get y is a times 2 exponent plus infinity. Now, when x goes to plus infinity, 2 exponent infinity is going to be a huge number, but since a is negative number, negative times a huge number gives you negative huge number, which is going to be negative infinity. Again, 2 exponent infinity gives you infinity, and then times it by a, which is a negative number, gives you negative infinity. So this means that the other tail of the graph is going to be somewhere around here. Connecting the points together, we get a graph like this one. Now, in this graph, you can see that your a is your y-intercept, which is the coefficient here, and the domain is again all the real number because there is no restriction on the x value, and the range this time is y such that y is in R and y has to be less than 0 because y is all these points down here. And again, your x-axis is going to be your asymptote. And also, if you look at this graph, you can see that when you are moving from left to right, the graph of the function is decreasing because the y value is getting lower and lower. You always look from left to right to see if a function is increasing or decreasing. Always left to right. And if we walk along the graph, point by point along the graph from left to right, you can see that your y value is decreasing. So the function is decreasing. The last case that we are going to consider is when a is negative and b is between 1 and 0 again. Again, for simplicity, let's assume b is 0.5. So y is equal to a times 1 over 2 exponent x. Again, our Cartesian coordinate system. Let's consider the case when x is 0. When x is 0, 1 over 2 exponent 0 is 1. So we get the y-intercept is a. Since a is negative, so it's going to be somewhere around here. This is our a. Now the next thing is when x goes to negative infinity, then y becomes a times 1 over 2 exponent negative infinity. If I flip it to get positive exponent, I get a times 2 exponent positive infinity. So when x goes to negative infinity, we get a times 2 exponent infinity. But 2 exponent infinity gives us plus infinity, but you multiply it by a, which is a negative number, so you get negative infinity. So this means when x goes to negative infinity, y goes to negative infinity too. So it's going to be a point here. Now, when x goes to plus infinity, we get y is equal to a times 0.5 or 1 over 2 exponent infinity. Again, using your calculator, find what is 0.5 exponent 100. You will see it's almost 0. And 0 times a is going to give us 0. So this means that when x goes to plus infinity, which is around here, y goes to 0. So it's going to be a point here. Connecting the dots together, we get a graph like this one. Now, again, the y-intercept here is a. The domain is all real numbers because there is no restriction on x. The range, again, is going to be all real numbers where y is less than 0 because all the y is here. And also, the x-axis is your asymptote. And this function, when I go from left to right again, along the graph, meaning this way, you can see that the y value is increasing. I start from negative infinity here, and I ended up to 0 here. So this means the y value is increasing, so the function is increasing. In the first example, we are supposed to plot the graph of y equal 4 times 1 over 2 exponent x. To do this one, again, we need 3 points. First, when x is 0, we get y is equal to 4 times 1 over 2 exponent 0. 1 over 2 exponent 0 is 1, so y is equal to 4. So this is our y-intercept here. The next point we are going to pick is when x goes to infinity. When x goes to infinity, we get 4 times 0.5 exponent plus infinity. We know that 0.5 exponent, the huge number, is going to give us almost 0. So y becomes 0. So it means that y is here, close to x-axis. And when x goes to negative infinity, we get 4 times 0.5 exponent negative infinity. But 0.5 is 1 over 2. And since I can write it like this, y is 4 times 1 over 2 exponent negative infinity. 1 over 2 is the same as 0.5. Since we have negative infinity, I'm going to flip it and change the sign so it becomes 4 times 2 over 1 exponent plus infinity. 2 over 1 is the same as 2. 2 exponent plus infinity is going to give you infinity times 4 is still infinity. So this means when x goes to negative infinity, which is here, y goes to plus infinity, which is somewhere around here. So the graph looks like this. Now, the domain, as you can see, is all the real number, x, there is no restriction. The range is all the real numbers for y, but everything which is greater than 0. The y-intercept is 4. If we walk along the graph from left to right, from here to here to here to here, you can see that the y values are decreasing. You start from positive infinity and you ended up at 0. So this means that this function is decreasing. The next function that we have to plot is y equal negative 3 exponent negative x. The first point is when x is 0, negative 3 exponent 0 becomes negative 1. So negative 1 is the y-intercept. Now let's consider when x goes to negative infinity. We have y is negative 3 exponent negative negative infinity. This becomes negative 3 exponent infinity. We know that 3 exponent infinity is going to be infinity times negative 1 is going to give us negative infinity. So this means when x goes to negative infinity, which is somewhere here, okay, y goes to negative infinity, which is somewhere around here. So this is another point that we are going to include in our graph. Now let's consider when x goes to plus infinity. We get y is equal to -3, negative infinity. Now, again, since this is exponent negative infinity and this is division by 1, I'm going to flip it. I get -1 over 3 exponent plus infinity. Now, if you use your calculator, try to see what is 1 over 3 exponent, let's say 100. But remember to use bracket. So when you're typing the number, type bracket 1 divided by 3 close bracket exponent in let's say 100. You will see that you will get almost 0. And negative times 0 gives you 0. So this means when x goes to plus infinity, which is somewhere around here, y becomes 0. So it's going to be a point here. And now I'm going to connect these points, and I'm going to get a graph like this one. Now, looking at this one, you can see that the x-axis is your asymptote, horizontal asymptote. The y-intercept is going to be -1. The domain is all the x values in the real numbers because there is no restriction. And the range is going to be all the y values in the real numbers which are less than 0. Now, if I start walking from left to right along the graph, you can see that I start from negative infinity and I ended up at 0 here. So this means that the function is increasing. The next question says, write the equation in the form y equal ab exponent x that describes the graph shown. Whenever you have a question like this one, pick the points which are on the graph and they are on the intersection of the grid lines. Meaning, for instance, I can pick this point which is on the graph and the intersection of the grid lines, and I can also pick this point which is the intersection of the grid lines and it's on the graph. And since in this equation y equal ab exponent x, there are two unknowns a and b, I need 2 points. So let's substitute the first point. The first point here, this is 1 and 6, and this point is, let's see, it's going to be 3 and 54. So I'm going to sub the first point when x is 1, y is 6. So when x is 1, y is 6. That's the first equation. The second equation says when x is 3, y is 54. Now I have these two equations and I have to find a and b. There are 2 ways you can do it. You can either isolate a on the first equation and then put it back in the second equation, or you can just divide these two equations together. So if I divide this equation here by the first equation, I'm going to get 54 over 6 is equal to ab cubed over ab. Now a crosses out with a, b cubed over b gives me b squared, which is going to be equal to 54 over 6 is going to be 9. Now we have to take the square root of both sides, so here is going to give us b is equal to 3. Now you may say, what about the negative one? Remember that we started this lesson by the assumption that b is greater than 0, so we cannot accept negative 3 here. So b is going to be equal to 3. To find a, I'm going to use the first equation for an example. So I get 6 is a times 3. From here I get a is equal to 6 over 3, which is going to be 2. So this means that y is equal to 2 times 3 exponent x. In the next example, we have a radioactive sample which has a half-life of 3 days. Now, if you, just to remind you, what exactly is a half-life? Again, as we said before, the half-life is the time that it takes a substance to lose half of its weight. For instance, this radioactive sample, which has 3 days half-life, this means it takes 3 days, so half of the radioactive material is going to being converted to another form of material. Now, the initial sample is 200 milligram. You're supposed to write a function to relate the amount remaining in milligrams to time in days. Whenever we are dealing with half-life, this means that our exponential function is going to have a base of 1 over 2 half, or 0.5. So I can write that m, which is the mass which is remaining at any time, is equal to initial mass, which is 200, times, again, because it's half-life, so it's going to be 1 over 2 exponent. Now, there are two ways I can express the time. Either I can say, if you give me time, let's call it t, in number of half-lives, this is going to be my equation. But in general, I'm not going to assign t to be the number of half-life. I'm going to give you t in number of days. This means that whatever number of days I give you, you have to see how many half-life of 3 days you have. For instance, if I give you 9 days, then you are going to say, okay, 9 divided by 3 is going to be 3 half-life, which is going to be the value that I have to substitute here. If I give you 21, you say 21 divided by 3, and then you sub it back in this equation here for t. So to make life easy, instead of expressing t in terms of half-life, I'm going to express it in terms of number of days. So I can write this guy as m is equal to 200, 1 over 2 exponent t over 3. Now, if you give me t in number of days, this division is going to give me the number of half-lives. So if I give you, let's say 21, then you say 27, then you say 27 divided by 3 is going to be 9. So this one, it takes care of the number of half-lives. Now it says restrict the domain of the function so that the mathematical model fits the situation it is describing. Since in this case t represents number of days, so my domain is going to be t such that t is in R and t has to be greater than or equal to 0, because you can't have negative number of days. And t can be real number. I can have 2.3 days or 2.758 days.